Hello everyone, so today is the 11th problem solving session of the course. Introduction to lasers. So I will start with discussing few problems and then I'll go into some topics, but let's just wait for a few minutes for others to join and then I'll start. Okay, so I am Bhaskar De and today is the 11th problem solving session for the course Introduction to Lasers. Now I will write down the problem and then we'll solve this problem. So the statement of the problem is pretty big, so I'll just write it. A hypothetical gas laser operates at 200 nanometer in cavity. Then with mirrors separated by 2 meter and is dominated by Doppler broadening with a Doppler with LWHM of 4 into 10 to the 9 Hz. The gain for a single pass through the amplifier is 12%, and each mirror has a reflectivity of 98%. And the transmission of 1%, and a scattering loss of 1%. There is also a scattering loss of 0.5% at each Brewster window. Now if this laser were mode locked, what would be the maximum number of modes that could contribute to producing mode locked pulses, and what would be the minimum pulse width of each pulse. What would be the separation between pulses? So this is the whole statement of the problem, which is pretty big. So here we are talking about a hypothetical gas laser that operates at 200 nanometer. 200 nanometer in a cavity with mirrors separated by 2 meter. So I am just circling all the important parameters given in the problem, and is dominated by Doppler broadening with a Doppler width of 4 into 10 to the power 9 Hz. The gain for a single pass through the amplifier is 12%, and each mirror has a reflectivity of 98% and a transmission of 1% and a scattering loss of 1%. There is also a scattering loss of 0.5% at each booster window. So these are the information that is given in the problem. Now The question is, if this laser were mode locked, so we know about the mode lock mechanism. So what would be the maximum number of modes that could contribute to producing mode lock pulses, and what would be the minimum pulse width of each pulse, and what would be the separation between pulses? So there are three questions. What would be the maximum number of modes that could contribute to producing mode lock pulses? So this is the first question. Then another question is, what would be the minimum pulse width of each pulses, and what would be the separation between pulses? So there are three questions and these are the parameters given. So now we'll write down the important parameters. That is, the first is the so now first I'll write down the parameters. The new d Doppler FWHM of the Doppler burning, that is 4 into 10 to the power 9 Hertz. Wait a second. So this is the 4 into 10 to the 9 Hertz. Then there is R, that is 0.98. Okay, so there is some problem with the pencil, I think, and that's why I cannot write properly. So please bear with this problem. Now R equal to 0.98, then T equal to 0. T equal to 0.98, sorry, T equal to 0.01. So now we will have A equal to 0.01 plus A equal to 0.01 plus 2 into 0.005, which will be equal to 0.02. So then from the transmission. So the total cavity loss is 3%. Okay, so just wait for a few minutes and I think the pencil will work. I'm very sorry for this. So I'll just explain the method here, so that will be beneficial for us. So here these parameters are given, that is the gain from the for a single pass. So the amplifier is 12% and each mirror has a reflective of 98%, so there is a 2% loss, a transmission of 1% and a scattering loss of 1%, and then there is also a scattering loss of 0.5% at each booster window. So the losses or cumulative loss is total 3%. So transmission is 0.01 1%, and then the scattering loss is 0.01, and then another scattering loss from the booster window, that is 2 into 3, that is 0.5%. so the total scattering loss is 0.01 plus 2 into 0.005 equal to 0.02, which is the total scattering loss. So total cavity loss is 3% per pass. Yeah. Okay, so I'll just write it in proper handwriting. So R equal to 0.98, T equal to 0.01, then the total scattering loss is A equal to 0.01 plus 2 into 0.005 equal to 0.02. So total cavity loss is 3% per pass. Okay, now we will calculate the GD new. GD. So GD new is the Doppler bonding basically. So here we will have basically gain. So this is given by ln2 by 16 pi cube c square a ul eta square nu d square delta nu d n u minus gu by gl nl e to the power minus 4 ln2 nu minus nu d whole square by delta nu d square. So at nu equal to nu d, gd nu equal to root over ln2 16 pi cube c square by nu d square aul by delta nu d. So at nu equal to nu d, sorry, nu naught, we have this expression, or e to e minus 4 ln2 mu minus mu d whole square by delta mu d square is equal to 1 when gain is 12%. Let mu minus mu naught equal to delta nu so e to the power minus 4 ln2 delta nu square by delta nu d square equal to 1 by 4 0.25 which gives to the power 4 ln2 delta nu square by delta nu d square equal to 4. So 4 ln2 delta nu by delta nu d whole square equal to ln4 equal to 1.386. So from here we have delta nu equal to 0.50 in delta nu d which is basically 0.707 into delta nu d which is 0.707 into 4 into 10 to the power 9 hertz which is 2.82 into 10 to the power 9 hertz. So here we basically did the so from the parameters given here we basically calculate the GD nu. So then we use the GD nu equal to 1 as when gain is 12%. So this is the condition at maximum gain. Then from there we calculated the value of delta nu and we get that delta nu is 2.82 into 10 to the 9 hertz. Now delta nu shape is c by 2d which is 3 into 10 to the power 8 by 2 into 2n. So the d is 2 meter. So this is the d. So the delta nu shape is this one 3 into 10 to the power 8 divided by 2 into 2 meter which will be 7.5 into 10 to the power 7 hertz. Now as we have the delta nu and delta nu shape we can calculate the number of modes. So number of modes is equal to, so we'll just divide delta nu by delta nu shape plus 1. So 2.82 into 10 to the power 9 hertz divided by 7.5 into 10 to the power 7 hertz plus 1 which will give 37.6 plus 1 38 modes. Delta t shape. So basically in this laser, so the question was that if this laser were mode locked, what would be the maximum number of modes that could contribute to producing mode locked pulses. So in this particular laser 38 modes are contributing to the pulses. Okay, so this is the answer is 38. There are 38 modes. Sorry. So 38 modes are contributing to the pulses. Basically 38 different oscillating sine wave are locked in phase, and that gives rise to this pulse. Now we'll calculate the delta t shape, which is the minimum pulse width of each pulse, which will be given by 2d by c, that is 13.33 nanosecond, and then the delta tp, which is given by 7.15 into 10 to the power 7 into 38, which will give 3.5 into 10 to the power minus 10 second. Okay, so in this problem, this is a huge problem. So where we are given the operating wavelength of the gas laser, the separation between the mirrors, the Doppler width, the gain for a single pass to the amplifier is 12%, and each mirror has a reflective 98%, transmission of 1%, and scattering loss of 1%, and there is also scattering loss of 0.5% at each booster window. So now from there we calculated the delta nu, the maximum number of frequency that is in the cavity, that is 2.82 into 9 Hz, and then the separation between this frequency is 7.5 into 10 to the 7 Hz. From there we calculated the number of modes, which is 38 modes, and then the delta t shape, which is 13.33 nanosecond, and then delta tp, that is 3.5 into 10 to the power minus 10 second. Okay, then I will move to the next problem. In a 3 mirror laser cavity, in which the laser is producing a clocked pulses at intervals of 12 nanosecond, the focal length of both M1 and M2 is 0.1 meter. What is the distance between M2 and M3. If the mode locked pulses have a width of 133 femtosecond and you what and you know that the laser is mode locked over the FWHM of the laser gain medium. What would you suspect is the gain medium? Okay, so in this problem it is not a problem of two mirror laser cavity. In general we have two mirror like this and then there is the gain medium, but here there is a three mirror laser cavity. So the diagram I will show later, but this is a three mirror laser cavity, so the gain medium is in between the three mirror in which the laser is producing a mode lock pulses. So it is given that the laser is mode lock at intervals of 12 nanosecond. So the separation between two pulses is 12 nanosecond. The focal length of both M1 and M2 is 0.1 meter. What is the distance between M2 and M3? So we need to calculate the distance between M2 and M3, and if the mode lock pulses have a width of 133 femtosecond and you know that the laser is mode locked over the FWHM of the laser gain medium, what would you suspect is the gain? So here it is a very intuitive question that from the given information we have to identify the material, which is relatively intuitive because you need to remember the evaluation of all the material, and which is next to impossible. Okay, so the first I will draw the laser cavity. So how does this laser cavity should look like? So here is M2, this is M3, this is M1. So this is the gain medium or the gain cell. This is the angle 2 theta. So this is the 3 mirror laser cavity. So here you can see there are 3 mirror, M1, M2 and M3. So apart from all the information given here, the one information is regarding the mirror, that is the focal length of M1 and M2. M1 and M2 is 0.1 meter. So we need to know the distance between M2 and M3. Okay. Okay, this is what. Somehow I have the same thing at the first page and the last page, but I don't know how. Okay, I'll just continue from here, so and ignore the drill on. So this is the 3 mirror laser cavity, and in the problem we are given that the focal length of both M1 and M2 is 0.1 meter. What is the distance between M2 and M3? So we need to figure out the distance between M2 and M3. The mode lock pulses have a width of 133 frames per second, and we know that the laser is mode locked. What the FWHM of the laser medium? What would you suspect is again? So and after that we need to identify the laser. So now for M1 and M2, F equal to 0.1 meter. Okay, and d delta t shape. So the separation between two pulses is 12 nanosecond, equal to 2d by c. D equal to 0.180 meter. So basically we have this 0.1 meter distance or the 0.1 meter focal length. So in this picture, if the picture is not exactly perfect, but this focus point is somewhere here. So these two mirror M2 and M1 is focusing the beam at the gain medium. So that means that the focal length is equal to the distance between mirror to gain medium or cell. Okay, so that so the distance of N2 to gain cell is 0.1 meter. So gain cell to M1 is 2F equal to R equal to 0.2 meter. So the distance from M2 to M3 is 1.80 minus 0.1 minus 0.2, which is 1.50. So basically what we did here, we did a very simple math, that is we take the whole distance as d and we calculated that value of d from the delta t shape. So delta t shape is the separation between the two pulses and that is given as 12 nanosecond. Now we calculate the total distance inside the cavity as d, and that d is 1.8 meter. Now the distance of M2 to gain cell is 0.1 meter. As I mentioned that the focal point is at where the gain cell is situated, that's why the distance from the gain cell to the mirror is 0.1 meter. So now the distance to gain cell to M1 is 2a, that is 0.2. Now so distance from M2 to M3 is just the subtraction of 0.1 and 0.2 from 1.8 and you get 1.5 meter. Now we will calculate delta nu shape, which is c by 2d equal to 3 into 10 to the power 8 by 2 into 1.8 equal to 8.33 into 10 to the power 7 hertz. Delta tp equal to 1 by nu shape n. So the delta nu shape is 8.33 into 10 to the 7 hertz. So the separation between the frequency is 8.33 into 10 to the 7 hertz, and then the delta tp, which is given by 1 by 1 over delta nu shape n, is already given 133 into 10 to the minus 15 second. So this is basically 1 femtosecond is equal to 10 to the minus 15, 10 to the power minus 15 second. So that's why the pulse width of 133 femtosecond is equal to the delta tp, and from here we will calculate. So this is gain gain bandwidth. Now, so from here we can calculate the gain bandwidth equal to 7.52 into 10 to the power 12 Hertz. So from this bandwidth we need to identify the material, and so that is something not possible. I showed this example for the numericals only, not this assumption thing or something like that, but here I can just mention then this gain bandwidth is for the material ND class. So if you want to remember, you can remember it, otherwise it's not necessary. Now I will discuss about some topic, and which I will start with a solid state laser. So solid state laser is a very famous kind of laser. So the point of using this laser is certain types of solid state materials have excellent properties as laser gain media. So they generally consist of crystalline or glass materials into which specific atom ions are embedded to act as the living species. Now the host materials must naturally be transparent at the laser wavelength to preclude absorption of the laser light as it develops within the gain medium. Now there are two kinds of material in the solid state material. One is the host material and another is the dopant ion. So the laser species are referred to as the dopant ions here. Because they are doped or grown into the host material, typically in the form of doubly or triply ionized atoms, as they integrate and intersperse within the host during the growth process. So now a solid state laser is often erroneously referred to as by mistake referred to as by its host material rather than the dopant ion. For example, a NdYAG laser is a laser in which the dopant ion is Nd3 plus added to the host material in the form of Nd2O3, and the host material is yttrium aluminum garnet YAG. So NdYAG dopant ion is Nd3 plus, which is added in the form Nd2O3. The host material is YAG, whose full form is yttrium aluminum garnet. This laser is sometimes just called a YAG laser. In recent years, however, other dopant ions that have been successfully doped into YAG, which is YB-YAG. So this is yttrium. The dopant ion is yttrium, which has a lacing action at 3 micrometer wavelength. YAG has a lacing action at 2.1 micrometer. Then thulium has a lacing action at 2 micrometer, and iridium at 2.9 micrometer. Now I will just write a table. Diode, pumped, solid state lasers. Wavelength, power, pulse duration, tape rate, application. Okay, so first we'll see the details of Q switch laser. Now I will write the wavelength, that is the first is 1320 nanometer, power is 0.4 to 1 watt, pulse duration is 5 to 20 nanosecond, depreciation is 2 into 20 kilohertz, application is then 1064 nanometer, on to 35 watt, 5 to 100 nanosecond, 1 to 100 kilohertz, application is solar cell scribing, texturing, diamond cutting. 532 nanometer, which is 0.5 to 20 watt power, 5 to 70 nanosecond, 1 minus 50 kilohertz. Marking, PCB structuring, drilling, cutting. Then 355 nanometer, which has a power of 0.2 to 10 watt, 5 to 50 nanosecond, 15 to 100 kilohertz. Lithography. Now we'll go to mode lock laser. 800 nanometer, power is 0.5 to 20 watt, 100 femtosecond pulse width, 80 megahertz repetition rate, multi-photon imaging, optical coherence tomography. Then 355 nanometer, 0.424 watt, 10 picosecond, 80 megahertz repetition rate is used in printing, cutting of foils. CW lasers, 1064 nanometer, 5 to 15 watt, 0.1 to 100 microsecond, 5 to 40 megahertz. Two to 10 watt. Now there is the pulse distribution is not applicable because this is for fully diode formed solid state laser. Application is water inspection, disc texturing, image recording. So all these data are from spectra physics. So spectrophysics is a very wide known company of manufacturing lasers, commercial lasers basically. Now we'll go into some details of few lasers. So first one is UV laser. So UV laser, the specialty of UV laser is that the UV laser was the first laser now that people have developed. So it operates at in a pulsed mode at 694.3 nanometer with an emission line with an emission line width of 0.53 nanometer. Okay, so the UV laser rod consists of a sapphire crystal, Al2O3 with chromium ions, Cr3 plus, doped in a typical concentration of 0.05% by weight. So at this concentration there are approximately 10 to the power 25 chromium ion per cubic meter. The UV laser is typically flash lamp pumped with pulse duration ranging from a fraction of millisecond to few milliseconds. The laser can also be Q-switched. The pumping absorption bands occur at 400 nanometer and 550 nanometer with an approximate bandwidth of 50 nanometer at each wavelength, and thus they match very well with the pumping spectrum of xenon flash lamp. So basically the xenon flash lamp is used to pump the UV laser. The laser is a 3-level system and therefore has a much higher pumping threshold than such 4-level laser system as India's laser. However, the UV laser does have an exceptionally long upper level lifetime of 3 milliseconds, which gives it an unusually high energy storage capability. Pulse energies of up to 100 joule are possible, although the pulse repetition rate is low, 1 or 2 pulses per second, and hence limits the average power. This limitation is due to the excess heat produced by the high pumping flux required to produce laser output. And the advantage of UV crystal is that it's hard and durable, has good thermal conductivity, and is chemically stable. UV laser crystals from which laser rods are cut can be grown with very high optical quality. So this is the first UV laser, and so here this is the two mirror, this is one mirror, and then there is a semi-transparent mirror, and this is the ruby rod, and this is the flash lamp which is used to pump the laser, which is spirally tied with the uh, ruby rod, and then from here we have the laser output. Now I will write the typical UV laser parameter. Laser wavelength is at 94.3 nanometer. Laser transition probability is 33 femtosecond. Upper laser level lifetime is 3 millisecond. Stimulated emission cross section sigma UL is 2.5 into 10 to the power minus 24 meters square. Spontaneous emission line width is 3.3 into 10 to the power 11 per second. Insertion density delta n UL is 8 into 10 to the power 24 meter cube. Small signal gain coefficient G naught is 20 per meter. Laser gain medium length 0.1 meter. Single pass gain e to the power sigma UL delta n UL is 7.5. Looping density is 0.05% by weight, and index of refraction index of refraction of cane medium is 1.76. Operating temperature is room temperature. Pumping method, Flaslan pumping band is 404 nanometer and 554 nanometer. Output power up to 100 joule per pulse. Mode single mode or multi mode. So one of the most important application of the Ruby laser has been holography. So application is in holography. Because of its very high pulse energy and reasonable coherence length, a high power version of Ruby laser can be used to record large volume holograms in a single laser pulse. Recording such holograms is much more difficult with other lower power lasers because multiple pulses must be used. Ruby lasers are used in measuring such plasma properties as electron density and temperature. They are also used to remove tattoos as well as skin lesions resulting from excess melanin. Now we will go to the second laser, that is ND-YAG. So neodymium-YAG laser, the ND ion when doped into solid state host crystal produces the strongest emission at a wavelength just beyond 1 micrometer. Okay, So the two host material most commonly used for this laser is ion are laser ion are uh, yttrium, aluminum, garnet, yttrium, aluminum, garnet, and another is glass. When doped in YAG, and the formula for YAG is Y3Al5O12, and ND crystal produces laser output primarily at 1064. The output is at 1064 nanometer, and when doped in glass, the ND glass medium lasers at wavelength range from. So this is for this one, and for glass it is at 154 nanometer to 1062 nanometer. Depending upon the type of glass used, ND also lasers at 0.94 micrometer and 1.32 micrometer from the same upper laser level as the 1.064 micrometer tension, although those tensions have lower gain. Now the ND laser has a 4 level system and consequently has a much low pumping threshold than that of the UV laser. The upper level lifetime is relatively long. Level lifetime is 230 microsecond, and 320 microsecond for ND glass. Okay, so population can be accumulated over a relatively long duration during the pumping cycle when the laser is used either in Q switching mode or as an amplifier. So there are multiple way of using NDI laser. One is flash lamp, pumped, Q switched, NDI lasers. Flash lamp, pumped, CW, NDI laser, diode, pumped, NDI laser, and then ND glass amplifier. So the diode pumped NDI laser is a generic version of diode pumped solid state laser, and so in this laser the Pumping is done by gallium arsenide laser because this diode has the ideal pumping wavelength for Nd3+ ion in the region of 0.8 micrometer or 800 nanometer. Many of the applications for diode pump Nd:YAG laser are in the green portion of the spectrum, making it necessary to frequency double the 1.06 micrometer laser output to 0.53 micrometer. So the output of Nd:YAG is 1.064 nanometer, and after frequency doubling we can have 532 nanometer, a wavelength near the peak of the response of human eye. So the cavity element of the diode pumped frequency double Nd:YAG laser is like this. So here this is the pump light, the input coupler, output coupler, Nd:YAG crystal, and the booster plate. So this is the diode pump Nd:YAG reading laser system, and this is a picture from the company Coherent, which is also a laser manufacturing company, Coherent Inc. So this cavity element of the diode pump frequency double Nd:YAG laser is shown here, and this unique element allows the operation of a two-mirror ring laser by taking advantage of the refraction of the laser beam at the output of Nd:YAG laser rod at the booster angle to direct the beam toward the output mirror. The doubling crystal could be mounted intercavity for high conversion efficiency. This laser produces single frequency output of greater than 10 milliwatt and a linewidth of less than 2 MHz with a consequently large longitudinal coherence length greater than 150 meter. So now I will typical neodymium YAG and ND glass. These are parameters. So the laser wavelength is 1064 nanometer. Here it is 1054 to 1062 nanometer. Laser transition probability is 4.3 into 10^3 per second, where it is 2.9 to 3.4 into 10^3 per second. Upper laser level lifetime is 230 microsecond. Here it is 290 to 340 microsecond. Stimulated emission cross section sigma UL is 2.8 10 to the power minus 23 meters square, 2.9 to 4.3 into 10 to the power minus 24 meters square. Spontaneous emission line width line width is 1.2 into 10 to the power 11 per second, and here 7.5 into 10 to the power 12 per second. Or 5 nanometer, where delta UL is equal to 28 nanometer. Inversion density is delta N UL is 1.6 into 10 to the power 23 meter cube, 8 into 10 to the power 23 meter cube. Small signal gain coefficient is G0 5 per meter, that is 3 per meter. Laser gain medium length L is 0.1 to 0.15 meter, that is 0.1 meter. Single pass gain e to the power sigma UL delta N UL L is 2 to 20, it is 1.3. Doping density is 1.4 into 20 per 26 per meter cube, and it is 4.6 into 20 per 26 per meter cube. Index of refraction is 1.82, it is 1.50 to 1.57. Operating temperature is 300 Kelvin. This is also 300 Kelvin. Pumping method is optical. Flash lamp or laser pumping bands is 300 to 900 nanometer. Output power is 1 joule per pulse and up to 10 kilojoule per pulse. Mode is single mode or multi-mode. Okay, so now the application of this ND laser has more different kind of application than any other type of laser. So ND laser is the most commonly used laser basically. So perhaps the major application is in various forms of material processing, drilling, spot welding and laser marking, because these lasers can be focused to a very small spot. The lasers are also used in resistor trimming and circuit mask and memory repair, as well as in cutting out specialized circuits. Medical applications include many types of surgery such as membrane cutting associated with cataract surgery, gallbladder surgery, cauterizing, gastrointestinal bleeding. Many medical applications take advantage of low loss optical fiber delivery systems that can be inserted within the body to deliver laser energy to the appropriate location. And these neodymium lasers are also used in military applications such as range finding and target designation, and other kind of application also. Now we'll talk about another ND laser, that is NDYLF. So this is neodymium doped. So we know about ND, but we don't know about the three letters after that. So lithium, yttrium, fluoride, NDLI, LIYF4. So this laser has an advantage over the NDR laser because its upper laser level has a lifetime approximately twice as long as of the NDR laser. So since diode pumped lasers are power limited, the longing pumping time allows twice the energy storage in this laser. So the transition here is this. Okay, so this is 4F 3 by 2 This is 4i13 by 2. This is 4i11 by 2. So if someone is wondering what are these symbols, so these are spectroscopic term symbol which I have discussed in the first 2 or 3 weeks, and also worked out some problems regarding that. Micrometer, and this is 1321 nanometer. So this is two are the reading of this NDYLF laser. Then the laser has many of the same applications as ND-YAG, but the frequency double version is very attractive as a pump source for a tunable or mode lock titanium sapphire laser, a 50 watt diode. So this is the 50 watt diode bar pumped multipass ND-YLF slab oscillator amplifier system. So this is the part for the oscillator, which gives a 26.5 26.5 watt laser, and then it is going into the amplifier, the gain module, and is giving the 54 watt continuous laser or greater than 50 watt full switch laser, and the m square is 1.15, which is a quantity to understand the beam quality. So this is the slab oscillator amplifier system, and this is taken from the Q peak lasers. This is also a laser manufacturing company. Now we'll go in the ND-YVO4 laser. So this is neodymium yttrium date. So neodymium doped yttrium date is a laser that has come into prominence because of its amenability to diode pumping. It's operates at the same wavelength as Nd:YAG but has several advantages over Nd:YAG. These include a 5 times larger simulated emission cross section and hence higher gain, as well as a 4 times stronger absorption cross section, a 6 times wider pump absorption band centered at 809 nanometer. I'll draw the so here it is a high reflector, then this is a aperture, then these are all dichroic mirror. These two things are the main. It is the ND-YVO4 in crystal. Okay, so this Then this is fiber coupled 40-watt bar. So basically in this particular system there is this is a recent version of the this NDYV04 or in neodymium yttrium vanadate laser we have, that is involves the modular frequency triple laser using dual rods, so which allows scaling of the output power. In this laser, 4 fiber coupled 40-watt 808 nanometer gallium arsenide diode bars are used to dual and pump two vanadate crystals. So these two are the vanadate crystal which are pumped using this fiber couple. This one, this one, this one, and this one, and these are the gallium arsenide diode bars. And now each of those bars has an output fiber bundle of 1.1 mm diameter and a numerical aperture of less than 0.1. A periodic resonator with a geometrical length of 1.3 meter provides 48 watt at 1.1064 nanometer in a TEM00 mode when operated in a Q-switched mode at high repetition rates. The beam quality is M square is 1.05 and the peak power stability is greater than 1% RMS over repetition rate. Now the interesting thing is that after the second ND yttrium vanadate crystal, it passes through the output coupler and focuses with, this is a 1064 nanometer beam, focuses with a lens to the LBO crystal which is used for second harmonic generation. Then we get 1064 nanometer and 532 nanometer, and then again it is used with a lens and it focuses on a LBO crystal, and we have the 355 nanometer. So basically here we have two critically phase matched LBO crystal. So LBO crystal is a LBO crystal is lithium borate crystal which is used for second harmonic generation. So when we use omega in the crystal, we'll have a 2 omega and so when you use 1064 nanometer here, we'll have 106 we'll have 1064 nanometer here and 532 nanometer, but here we are using this 532 again in the LBO, so we have 355. Sorry, this is not 355. This is So there are also other lasers like Alexandrite laser, titanium, sapphire laser, chromium, lithium, LiSAF laser, which is basically lithium, strontium, aluminum fluoride, and then LiCAF laser, which is chromium, lithium, calcium, aluminum fluoride laser. These are all broadband tunable laser. So broadband tunable laser means that we have a band at the above. If you look at this laser somewhere, then you will see that there is a band, then there is another band, then there is a state, and then there is a state. So basically here is a band from a state transition. That's why we have the broadband laser. Then there are other fiber laser, color center laser, and all those things. There are multiple lasers available commercially. Then we have the semiconductor diode laser, where we have the famous gallium arsenide laser. So semiconductor diode laser, we have gallium arsenide laser, then indium phosphide based laser, then zinc selenide laser, gallium nitride laser. So these are the semiconductor based laser. The laser we have in our lab is YBKGW, which is yttrium doped potassium gadolinium tungstate. So this is the laser we have that gives us a 50 kilohertz repetition rate and 30 nanometer wavelength and almost some 100 femtosecond pulse width. So today I will end here, and in the next, as I have mentioned multiple times about the frequency doubling, second harmonic generation. So in the next class I will discuss about this thing and try to have some problem regarding this. So these things are not necessary for this course, but as we are talking about the laser, which is a intense which is basically an intense electric field. So from that we will have this kind of non-linear effects. So basically after the development of laser, we see this nonlinear effect frequently in the system. That's why we need to study these things, but I'll try to have some problems regarding this, and in the next class, if you have any doubts, you can join and ask me. I'll try to resolve those doubts, because the next class will be the last class of this course. So if we talk about the nonlinear optics, I'll just start a little bit. So in general, the polarization is proportional to the electric field, but when the electric field is increased significantly, nonlinear interaction begins to occur within the material to the extent that this equation is no longer valid, and we have to use this equation in order to understand the mechanism, that is chi1 e plus chi2 e square plus chi3 e cube plus dot dot dot. So here this is a scalar quantity basically, but when you are talking about here, this things are tensor. And also here it is a scalar quantity when we have a symmetric isotopic material, and it is a tensor when we have a anisotropic material. So this is it for today, and I will discuss about the nonlinear optics in the next problem solving session and try to find solve some problems regarding the nonlinear optics. Thank you. Thanks for joining. I'll end today's session here.